you know, people who do CFD and stuff like that, those kind of it's a lot of engineering type that those guys do. So those are probably the two most popular ones. And then of course there's my book that does all of those research stuff. It's relatively new.
So once they've plugged in, so you just either press PC or laptop. Yeah, so you just have to make sure that once it's plugged in, you tap PC, and it will automatically do it. No, it's logged in already. Yeah. There's a guest login otherwise.
Okay. Right. Is that all right?
Yeah. Yeah, simple.
Can I borrow your adapter, Brendan? Can I borrow your adapter?
Does it work? Oh, really? It works on a. So Microsoft is now Apple compatible. See my little book.
Can I get a copy?
This is my only copy. Can't have this.
Just a couple of announcements maybe. We've had a number of people interested in the project who are involved, who want to know more or even join as associate partners, which you will have heard a little bit about already. Best way to do that is to send me an email message and we can progress the discussions. I was told that on the table now, in addition to what were the questionnaires previously, which we will be nagging you to complete by the end of the meeting, you should have a sheet somewhere, and tell me if you can't see it, which is where you can ask a question. It's like question time if you know this format in the UK. You could put a question down. You don't have to do this, but for the panel discussion that follows this session, if you have a question, you can put it in the box which is at the top there by the exit. Do that by the tea break. All that does is enable us to sift a few of those in order to promote the panel discussion, which I really want to be an interactive thing. I don't want the panelists stating their views again. Just we'll get on with the discussion.
No matter how good their views are.
No matter how good they are. Right, with that said, this is the third session. It's entitled Cloud Computing for Biomedicine. We've got a stellar list of speakers. And the first is Booth, as they call him, Brendan Booth, who runs HPC cloud capabilities, etc. for Amazon Web Services.
Thank you, sir. Thank you. So I come from the online book and decorative pillow company, but I look after the research computing group inside Amazon. So it's our task to make sure that the cloud remains forever useful to folks like you guys who are trying to use it for, wanting to use it for science. And, the title of my talk asserts this point that I firmly believe, which is that when it comes to finding a platform for doing science on, I think the cloud is hand meets glove. And the reason for this is, as Aristotle bestowed to us a little while ago, slightly before I was born, the scientific method works, right, as we know. I think Richard Dawkins put it very bluntly recently that it works. Did everybody see that YouTube video? Good, I hope so. Anyway, I won't repeat his words because they're a little more blunt than mine. Anyway, it works, and it gives you, constantly iterating through this loop of making a prediction, testing it against the universe, refining your model, and going through. It gives you a tighter and tighter grip on reality, right? At least gives your model a tighter and tighter fit with the world. And it's an iterative approach.
You have modeled before hypothesis.
Well, actually, you're right. Hypothesis, it's a circle. The point is, it's a circle. So, the cloud is really doing this. It's embodying this in computational form. when you go out to do your research, you set out on the research program, you don't know, you can't predict 3 years in advance what kind of computing platform you're going to need 3 years from now. You won't know what the memory to core ratio is, and we heard a fair bit this morning about memory to core ratios. You're not going to know what memory to core ratio is actually the appropriate one for your code 3 years from now. You can't tell. You're not sure if GPUs are going to be the right tool for the job 3 years from now. You can't tell, whether FPGAs might be a major breakthrough for you or not. So being able to iterate and in a fairly agile way choose different resources and different tools is actually crucially important. The other thing that's crucially important about this is that your science progresses around about approximately with how fast you can iterate through this loop. If doing the actual simulation part, which might be, the simulation might be, map onto the experimental component here, in a computational sense. If doing that part requires putting in a merit allocation request, waiting a few months for a reply, waiting for a week to go by to get your job to the front of the queue, and then getting your 12 or 18 hours of execution time, that's actually going to be a pretty slow way of iterating through this cycle. So there's a few things that come out of this. Failure is a data point. When something doesn't work and it doesn't match the universe, that's actually a data point, actually tells you where to go. But the other thing is indeed just what we're aiming to do with the cloud, and this is really the large-scale purpose of the cloud, both to business and to science, is that we're trying to make failure quick and cheap and easy. We're trying to get you to that point where your model breaks. Your model doesn't predict the world very well. You find out what change you need to make to iterate through your loop again. And so our mission really is to lower the cost of failure for you, who are the practitioner using this tool. So, and thus we get this thing to spin around a little faster, and you can iterate and get to your science a lot faster. There's another, I'm shamelessly stealing this graph from my friends at Ulcers. There's another element to buying and building chunks of hardware, which is that the buying takes almost as much time as the building, and then that consumes an enormous amount of the life cycle of the machine. This is a fairly typical HPC acquisition plan, which might take 550 days. That to me that's pretty long. It's about 1.5 years worth of expended time. Whereas if you were to spin up something like an Ulcers cluster out of our app store, out of the cloud app store, you can have something running in a few minutes. And so within a few minutes, you could be actually doing your compute rather than waiting for it. The Ulcers folks have done a very good job of packaging all this stuff up, and then sticking more than 1,000 applications actually ready to use at the end of that food chain. So naked shameless plug, but thank you to those guys for doing it, because I think it's I think this is totally changing the equation. What that actually means is that it gives you guys the ability to focus more on the science and not the servers. We think that should be your objective. The servers should be a thing that just get out of the way. It also means that what have you got left? What is the infrastructure of the 21st century for science? It's not boxes in racks. It's data sets, tools, and techniques, right? We invest a lot of time, effort, and resources in standing up large public data sets for folks to use. TCGA is a good example, a controlled access public data set for the Cancer Genome Atlas. A lot of genomics ones, there's a lot of satellite data ones. The reason we put these in there is because if you guys are going to go and spend, $500,000 buying a bunch of hardware, a bunch of storage hardware, so you can have a copy of a petabyte-sized data set, well, if we imagine that there's a lot of people around the world doing that, owning copies of the data set doesn't give you an insight. Owning a shelf full of books doesn't make you smart. Reading the books does, or potentially does. Processing the data potentially gives you an insight into the universe. Owning a copy of the data does not. So if we can own a copy of the data for you, and give you access to the data for free, and you can spend your money instead on the CPU cycles that are processing that data and getting an insight, then we've changed the world. Right? And that to us is a much better way of doing it. So we invest a lot in putting up public data sets. We also invest a lot in trying to overturn the paradigm that we're already working in ourselves. I think the first line of this, cannibalize your own products or somebody else will do it for you. We're looking to make sure that you don't have to, this is one of our experiments that we're doing, is to see if we can actually get you to stop thinking about servers. Servers and libraries. You should be thinking about code. So what we've come up with is a thing that we call AWS Lambda, which is where you deploy code into the cloud, and you actually you let us orchestrate the execution of that for you and give you the result. And these can actually be event-driven routines. So there's a bit of Python, might be a bit of Python you deploy into the cloud, and it gets picked off by an event. And we have a lot of events that go on in the cloud. Events could be billing alarms, events could be a bunch of data that just arrived in a storage bucket. An event could be that a job finished running on some other platform. That might be an event. And then those functions themselves can either be doing some compute, processing some genomic data, doing something meaningful, or they could be orchestrating other events to occur. So you could actually have a dynamic HPC cluster being sprung into life in response to the arrival of some data that is, that's actually that needs processing at a large scale. And whilst that data is not there, neither is the cluster. And so when you think about the economics of how to preserve your research funds, not paying for a cluster when you're not using it is a pretty good one. That's going to save you a heck of a lot of money. So, and money, by the way, which you can spend on postdocs, PhD students, people that can do meaningful work. So a good example of this is a really good use case of Lambda. Some folks at CSIRO in Australia, they use Lambda to actually implement, it's a CRISPR off-target, it's an off-target search workload. Now, I'm not a bioinformatician, I'm not a biologist, so so forgive me, I'm a recovering astronomer, and I've recovered quite well, by the way. So what they did with this workload, instead of actually having servers sitting around all the time waiting for a request, or instead of even having servers running, at the scale that they need in order to get the job done in a reasonable amount of time, and they had a 2 to 4 minute return on a job as their target for it to be useful in the environment they're working. They implemented it as a bunch of Lambda functions in the cloud. And so when they actually need to kick off one of these things, about 1 billion calls get sent to Lambda of 1 or 2 functions. The results get accumulated by another function, and then the result gets spat back out. They implemented the entire workflow in a bunch of serverless functions. The really cool thing about this is that no matter how many jobs they throw at this, we actually expand the fleet of hardware in the back. We orchestrate stuff in the back behind Lambda. So whenever demand goes up, we throw more resources into Lambda. That's up to us to optimize. The result that comes out of it is these guys have got a service running that gives them a better than 2 minute return time, and it's costing them $15 per month. $15.70, they tell me. A few other ways that we can change the way that computing is done. Notebooks, everybody knows about notebooks, of course, and in fact I saw some people plugging away working on some data this morning in between the talks. The ability to take something in a notebook format from your laptop and push it up into a server, push it up into the cloud, you can push it onto some GPUs, you can push your data onto a cluster in the cloud, and all of that stuff can be done dynamically. You can try before you buy. You can figure out if the cloud's going to work for you by spinning up a small cluster and seeing if your code will scale and give you the results that you're expecting, or at least give you the performance results you're expecting. So we do all of this by having a very large global infrastructure. We just announced last week that or the week before, sorry, that we're opening up a new region in Stockholm. Later this year, we'll open up one of the regions we're constructing in Paris. We've already got them in London, Dublin, and Frankfurt, and then we're expanding elsewhere around the world as well. We've got some more announcements coming in coming months. This is a very large infrastructure. In most, and the way that we arrange our infrastructure, we group data centers together in things called regions. So a region for us is a collection of availability zones. These are things that are fault tolerant to each other, or at least have different fault tolerance characteristics. That allows our customers to be able to build different services that they might want to construct, like say DNA Nexus have opened up a workload in our Frankfurt region. When you push something to DNA Nexus, they actually straddle across multiple availability zones so that they can be sure to have something that's always up when you're expecting it to always be up. And then inside those AZs, inside those availability zones, are data centers themselves. And then inside those data centers are usually tens of thousands of servers. And so these are extraordinarily large pieces of infrastructure. James Hamilton, our chief engineer, blogged the other day that a typical infrastructure investment for us in the region is in the neighbourhood of $200 million as base case. So, so you get the idea. This is a very large piece of infrastructure. We do something rather unusual, which is that we make all of our spare CPU cycles that we have available in all of these regions available in an auction market. And for scientists, that's actually a pretty attractive thing. The auction market is attractive because you can name your own price. So it's kind of like an eBay for CPU cores. So this will get you a vast amount of resources in the order of, say, around about a cent per core hour is a fairly normal price to be paid in there. What's interesting is that you can drive some extremely large workloads. So these are the guys at Fermilab. One of my favourite examples. They used just shy of 60,000 cores over a weekend to process a large backlog of data. This is our spare infrastructure in one of our regions in the US. So often our spare capacity is larger than most people's actual capacity. 60,000 cores would pretty much. How many cores at Archer? How many cores has Archer got? 120,000. So we're not doing too bad, right? It's a fairly large and respectable amount of spare capacity. So anyway, we break all of that up into a large number of different instance types and different services. So this is an eye chart. We could do a test. We could do a pop quiz on this later if anybody wants to try and memorize it. But there's basic things in there like servers, storage, and networking that you can bolt together into solutions yourself. Or you can take some solutions just off the shelf that are pre-canned, like a database. I want a SQL database now. You get a SQL database and you can start doing SQL. I want an HPC cluster now. I would like a MapReduce cluster now. And the really cool things about this is this gives you the ability to actually experiment. Again, this gets back to the cloud as being a computational environment for experimentation. You can wake up in the morning and actually theorize that your workload is going to be assisted by maybe a MapReduce approach, and you can give it a try. You can spin something up by lunchtime, give it a whirl. By the end of the day, you can be convinced one way or the other that this is either going or not going to work. And gives you the ability to do that experimentation. Our compute platform, it's a bit of an eye chart. You can't read this. I really do challenge anybody to read this. And it's not the full list anymore. We've had some new instances come out, and we've got some more coming soon, so it'll become even more unreadable. But it gives you the idea that no matter what kind of compute problem that you have, you will find a platform in there that you can experiment on. Large memory, small memory, high I/O, low I/O, sequential I/O, random I/O, GPUs, FPGAs, all of these kinds of things. So we're experimenting with all of these things ourselves because we're trying to work out how to solve some of our own problems. With more than 1 million customers around the world, everybody's got a different workload. It's important for us to have a large amount of speciation, I guess, in this space. We do everything through the user interface, of course. There's a nice, pretty web interface for doing this stuff. It's actually pretty easy to create servers and create clusters through a web interface. But we also believe in making all of that available as code as well, whether that be an API endpoint, so everything that you can do through the user interface you can do with an API or a command line, and in fact quite often you can do more than you can do through the user interface. The reason for doing that is that code is more reliable than people. And the other good thing about it is when you solve a problem once, it stays solved. So you write a script that spins up a cluster that has a particular branch and variety of software and resources on it, and you can come back to that anytime you like, a year, 2 years later. You can just come and spin that stuff back up. 7 years later, you can come and spin that same stuff back up. It also means that you don't make mistakes. If you're spinning up a cluster to do some work this week, turn it back off, and then come back a semester later, you're not going to make any mistakes in reproducing that environment. You can just pull it out of the freezer, and it's ready to go again. It also means you don't make it. Not making mistakes is also very important for security. I heard security come up a few times this morning. Security is critical, right? So security is our #1 priority. At a global level, we can't afford to be lax with security. So that would be an impossible outcome for us. We have to be more paranoid than our most paranoid customers. We have banks. My bank back in Australia actually performs most of their transactions and most of their work in the cloud. In a highly regulated banking sector like that, the ability to actually put banking applications in the cloud means that our security has to be super tight. And our ability to comply with those requirements has to be super tight. We carry clinical data, we carry patient identifiable data in the cloud. The way that we do that is we have these things called quick starts. Right? Quick starts are a really neat way to get environments set up automatically. So for instance, if you're working with data that has to be classified as UK official, it has to be treated in a UK official manner, you can spin up a UK official environment in the cloud that gives you all of the controls, all of the access functions, audit methods, and compliance strictures that you might need in order to hit that standard. And we have yet another eye chart that's got all of the logos for all of these different types of standards we have to meet in different environments around the world. Cost control and budgeting is something that always comes up. Everybody's wondering, well, this stuff costs money. How do I make sure I don't spend too much money? That's actually a very good question. We're actually more enthusiastic about trying to figure out ways of saving you money than we are in trying to drain your wallet. It would be a happy thing for me if everybody stopped buying too much physical infrastructure and used the cloud. It'd be an even happier thing if everybody net spent less on infrastructure and more on science. Right? That to me is a much more noble objective. So we have a lot of tools that are built into our interface to help you control your costs. We have some new tools that we've implemented that allow you to limit your spend. And so I will shamelessly promote this book, written by a very good-looking author. Anyway, this book has got most of the tools that you are likely to need, or at least it's a really good start for getting research work going in the cloud. What's most interesting about it, the tools in here will actually show you how to put a lid on your spend. So if you've decided in advance that your spending cap is going to be $100 a month, you can put in a $100 per month cap in there. You'll get notified as you progress towards that number. And when you actually get to that number, it will trigger a function which will shut everything down. And if that's a good outcome, or if that actually means that you've got that financial firewall in there so that you know you're not going to trip over a budget limit, and that gives you that should give you a much more comfortable and safe space in order to play. The book also takes you through some steps to make sure that your data is secure as well, and that your account is set up in a properly secure way. So there's a lot of that inside the book. There's also a lot of other stuff inside the book that will actually help you understand what solutions are available once you're in the cloud. Everything from clustered file systems to ALSys flight, HPC clusters, DNA Nexus, software as a service portals, any number of different things. Right. So anyway, so I'll sort of leave it there. If anybody wants a copy of the book, there's a URL there. You can go and register, download a copy online, and get cracking. 152 pages of goodness. Anyway, I think I'll stop there. Take a breath and take questions.
questions?
Can't read the author's name.
Pardon?
I can't read the author's name.
Anything else? If not, thanks again.
Great.
And
Thank you.
we'll move over to the next speaker. So let's make sure the mic gets transferred to
Got the thing there.
Matt.
Put that on the top.
This is the CTO. Is that ready? I think so. How do I make this possible? From beginning. Okay, yes. Where is a plug? There's a plug. Do you want to stick it in? It's a clicker. Okay.
Right, the next speaker is Matt Harvey, who's the Chief Technical Officer of Accelera, for whose purposes.
Yes.
And Accelera is an SME, which is a core partner in the Biomedicine project.
That's right. Thanks, Peter. So, as Peter says, I'm the CTO of Accelera, but many of you here will probably also know me, different hat that I wear, working for the Research Computing Service at Imperial College. Accelera is, as Peter said, it's an SME that I co-founded around about 10 years ago, which the rationale for that was to commercialize a particular application which we developed, which is called ASEMD, which is a classical molecular dynamics application some of you may have heard of, maybe even used. It's very similar in function to NAMD, which Peter talked about earlier, but the distinguishing characteristic of it was that we developed it from the ground up for GPUs, which then at the time seemed to be a very promising technology for high performance computing. And indeed, with this code, we were able to do something which was quite a qualitative change in terms of the level of simulation that we could access for a given budget, because instead of having to use a high performance computing system of the traditional cluster type, we were able to achieve a comparable level of simulation on just a single GPU, which, although doesn't give us more insight at the level of an individual simulation, we actually were able to obtain much more simulation or level of investigation onto the system that we're modeling for the same amount of cost, simply because GPUs were several orders of magnitude cheaper than comparable HPC hardware. So it played its part in really revitalizing the use of MD, certainly in the biomolecular space, and it led to the possibility of being able to commercialize this activity, to undertake a transitional activity from taking MD out of the lab where it really had been in use in a very limited scope for almost 2 decades by that point, and apply it in industrial contexts. And when we started doing that, we very rapidly found that we encountered 2 main pain points in engaging with industrial clients. The first was that it was a simple issue of resourcing. Many organizations, though they might have had their own HPC systems in-house, often they did not have GPUs, which were absolutely essential for running our application. And they, furthermore, weren't really predisposed to making a big capital investment in quite a novel sort of hardware for what for them was a speculative activity. So we thought initially that we would address that problem by relying on the HPC resources available throughout the community, through academic centres and other centres. But we rapidly found that although that was technically feasible, as soon as we proposed that to the IT security people inside a pharmaceutical organisation, we really ran into the mud pretty quickly because it really proved very difficult to be able to provide the level of information security demonstrate the level of compliance that these organisations needed on the sort of infrastructure that we were providing. So we really had to go back to the drawing board and think about how we were going to remove these pain points and be able to deliver the computing resource that these guys needed in order to be able to take advantage of the sort of systems, sort of solutions that we were proposing to them. So very rapidly we alighted on AWS as the ideal infrastructure for providing this type of resource. To give you an idea of what this level of resource was, an individual experiment of the type that we typically do, Peter described very ably earlier the type of methods that we're using. So these are ensemble MD methods, which are quite computationally expensive and designed to provide some insight into a binding affinity or a binding pathway or close. The exact details vary depending on what we're doing, but it's roughly 10 to 100 GPU years of computation over the course of maybe 4 to 6 weeks in order to complete one of these studies. So we needed an infrastructure in which we could deliver quite a large amount of compute, but for quite a short period of time, because it's important not just to be able to deliver an insight, but you have to do it in a timely manner. If one doesn't get a result in time to inform some business decisions, say in the context of drug development, a computational study is useful only to the extent that you can use it to inform maybe a synthesis or some other investigation. And so you have to be able to fit this type of analysis into a broader business or development cycle. So timely computation is very important. This infrastructure that we built, this product Ace Cloud, is basically our software layer, which is very thin on top of AWS, that facilitates and orchestrates the execution of our software on cloud resources in such a way as it's very straightforward for an end scientist to use, and it also integrates quite well with the organizational requirements of the organization's IT department. So, as I said, our goal is to build something which is flexible. AWS provides access to such a large infrastructure that we can scale out very rapidly from running just a single simulation up to hundreds of simulations without having to book any time in advance or schedule resources in advance. They're available on demand when they're needed, and then they go away when the need is gone and one incurs costs only while they're in use. Security, as I said, is tremendously important when looked at from an industrial perspective. So it was tremendously helpful to be able to point to the standards compliance of the AWS infrastructure. And so that effectively avoided a whole conversation about us having to provide software infrastructure or demonstrate to the potential client that our own infrastructure was audited and compliant with the expectations that they had. And all of our software, or Ace Cloud, runs entirely inside the customer's own AWS account. So there's no third-party software involved. There's no transfer of their confidential data outside of their administrative control. Of course, it's reliable. The AWS infrastructure is highly redundant. As Brendan said, there are many different independent regions and zones. We can deploy into any or all of those at the same time. And because the infrastructure is so large, one can, with a high degree of confidence, know that you will get your results in a timely manner, and you're not going to be preempted by some other user who is using or resources which you are contending for. You're never going to submit jobs and discover that they're queuing and queuing indefinitely as they might if you were using your own internal and finite-sized HPC resources. We're able to work in quite a cost-optimized way as well. As Brendan mentioned, AWS has the concept of a spot market, so we're able to place the jobs that we need to execute in whichever region in AWS happens to have the optimal spot pricing. So overall, we're able to minimize the, let's say, the number of nanoseconds of simulation per dollar that we can deliver this way. And generally speaking, what we need to deliver is to optimize the amount of sampling that we are doing for a given price. In the same way that previously one might have tried to optimize the amount of computation one could do in a certain amount of time on a traditional HPC resource. So here we're really looking at a cost optimization engineering activity. Now, all that sounds really good, but you also need to have something which is, for the end user, quite easy to use. Many of our potential users were very familiar with an HPC style environment. So one mode of interacting with the cloud through AceCloud is an environment which strives to be as similar to a conventional HPC batch processing environment as possible. But of course, this is just a component in a larger application stack that we have. So for many users of our software, one doesn't interact directly with the cloud resources at all, but are rather executing quite high-level workflows which are transparently or seamlessly executing intensive tasks either on local resources or in the cloud, depending on how things are configured. So to just dive into what the interface looks like, if you were installing AceCloud now and you wanted to start running simulations from the command line, then you'd use a simple command line tool, AceCloud, which performs the functions analogous to the QSub, the QStat, and the QDel that you might have on a normal HPC system. There are a couple of distinctions from a conventional environment that you might notice. The first is that we don't use job identifiers which are given to us by some batch system, but rather we have the ability to use our own identifiers, and those identifiers for each job have a hierarchical structure so that we can manipulate one individual job or a large number at the same time. And this makes sense for us because most of our work is ensemble based, so sometimes it's relevant for us to refer to an individual simulation and inspect the state of that, but often we want to do collective operations on tens or hundreds of simulations. And digging a bit deeper to look at how it interacts actually with the AWS infrastructure. So Brendan put up that lovely slide that shows the constellation of AWS services. We only really use 3 of those, which is S3, storage system, which is an online, effectively it's an object storage, one can put data into it through the web and then retrieve it again. EC2, which is the infrastructure for accessing compute resources, and then this one, which is best expressed as the box around those two, the virtual private cloud, which is a software-defined infrastructure, the software-defined network, which contains all of those resources that we're creating. So from the perspective of the end user, from their own workstation, when submitting a job to AceCloud, they start off by preparing input files. Well, if you've ever run an MD simulation, you'll recognize those files. If you haven't, it doesn't matter. But suffice to say, you prepare a job, you then submit it, much as you would do a QSub with AceCloud submit. Behind the scenes, this software goes away and it copies all of those input files that you've given it into S3, and it then instantiates a virtual machine running in EC2 infrastructure, which is backed by the GPUs that are needed to run our simulation, and also packaged with our software. This comes through the AWS marketplace. It's something which is like a canned environment that one can instantiate. Our software then, ASMD, starts up, it copies the input from this S3, it runs the simulation, periodically it puts the results back to S3, then when it's done, it closes down and the virtual machine which it was running on closes down. At that point, all of the resources in the cloud that you've been using are terminated, so you're really only using those resources when you need them for the simulations. There's nothing persistent here, you're not paying for some compute resource to sit around idle and to be available when you need it. The Amazon infrastructure is sufficiently large that you can be reasonably confident that you can get the resources as soon as you request them, which means that when you do an ACE Cloud status to see whether you're running jobs, you'll see jobs running or finished, but you'll almost never see them in a queuing state, which is probably something you're very familiar with if you've used an HPC system. So I said that's one way of using ACE Cloud, but also it's available directly through our higher level software. We make available as open source software something called HTMD, High Throughput Molecular Dynamics. It's a toolkit which we use for building all of our higher level protocols and services. It does everything that you need for MD modeling through the creation of models, the execution of simulations, and subsequent analysis of trajectories. So this is quite a verbose script which you don't really need to know the detail of. Suffice to say that what it's doing is preparing and running a single MD simulation, and the bit in bold shows where the simulation is going to be run. In this case, it's going to run on one's local GPUs on one's own workstation. But say you haven't got any of those, or you want to run a large number of simulations rather than just the one. Well, you simply change that to ACE Cloud Q, and the software will do everything necessary to talk to AWS, the ACE Cloud, and your simulations are run just as if they were, effectively just as if they were running on your own workstation. So, saying a bit more about how ACE Cloud is working from a security perspective, really from how we're using the AWS infrastructure. Everything is happening inside a single AWS account, and that means that no data is coming via any server that we run. There's no web server that's an Accelera web server which is talking to AWS on behalf of the client. All of that communication from the client through to AWS is directly through AWS APIs, which means that you get encryption for free, and if you care particularly about security, every one of those operations is auditable, and you can produce a complete log of every transaction that happens, so you can say with a high degree of certainty who did what, when, and what data moved. And this is just something that is not built into our product so much as something that you get entirely for free, in inverted commas, by using the AWS infrastructure. And as I said, we use we're able to use the spot market for cost optimization. Now, Brendan explained how that works in a high level, but what he didn't mention is that every one of those Amazon zones in AWS, regions and zones, have a different spot price because they're geographically distributed around the world, so there's a diurnal cycle to the demand on their infrastructure. And that means that if one is prepared to run one's work anywhere in any of those Amazon data centers, then you can choose to place jobs where the spot price happens to be cheapest, and our software is able to take a holistic view of all of the Amazon regions, place jobs wherever the spot price is cheapest, so we can be reasonably sure that we're always going to get something which is much closer to the floor of the spot price than we are to the on-demand price for the infrastructure. And that makes a really big cost saving. There's something like a factor of 7 between the on-demand price for resources and what we might get through the spot market. For this type of application, that can be the difference between an activity being cheap enough to be something that one does routinely as part of one's work, against something which is prohibitively expensive and something that you would only do as an exceptional activity. So till now I've described Ace Cloud as being something which is for running AceMD, and indeed that's first and foremost why we designed it. But once we had this tool, we really rapidly discovered that there was lots of other uses for it as well. Indeed, any computationally intensive task, it simply became the default option would be to add this to the Ace Cloud capability, so that pretty soon all of our intensive compute activity is something which we were doing on the cloud rather than locally on a local cluster or workstation. And one of the applications which I think shows this quite nicely is a tool we have for producing parameterization. So if you're doing an MD simulation, you need a set of parameters which describe the physics, the chemistry of the system that you want to simulate. There are sets of predefined force fields, predefined parameters for proteins and DNA and solvents and so forth. But if you're looking at small molecules, which if you are doing drug design, you almost certainly are, then you need to go off piste a bit and start to produce a parameterization specific for your molecule. And one way to do that is to fit the force field model against a whole set of QC calculations which describe the electronic structure or energy of a large set of conformers of the molecule that you're interested in. So this is can be a really expensive activity depending on the complexity of the molecule, requiring a large number of independent QC calculations. So again, this is something which one can either do on one's workstation or on a cluster, or again on Ace Cloud, and it's a simple matter of changing the execution target to tell the parameterization tool where it's going to run those QC calculations. And you can get a really big speed up this way. If you do everything in line, then each one of those quantum calculations may be say 40 or so, depending on the size of the molecule. Each one of those has to be computed sequentially. If you go to a cluster or a cloud, then you can do all of those in parallel at once, so you get a much higher turnaround. And for this type of activity, where you have a small number of parameterizations to do, maybe you're only interested in studying one or two molecules, you can really turn this from an activity which is going to block the rest of your work for several days, if you only have access to a workstation, to getting it done in the time it takes you to go for lunch, if you're able to fully parallelize on the cloud. Someone earlier asked Peter about the possibility of doing hybrid calculations using GPUs or CPUs for MD, and we've taken the view that increasingly the MD layer is something in which there's no particular distinguishing characteristic. The MD that we do is very straightforward. There are lots of different codes which can do MD just as well as AceMD now. So we have support for GROMACS and for AMBER and other MD codes, and really the choice that one makes depends on one's familiarity with a particular code, but also the cost effectiveness of using a particular code, which is a function of the type of resources that you have access to. So GROMACS is something which can run on GPUs or CPUs. If one has access only to CPU resources in-house, then one may choose to use this as well. And it's also very useful to be able to switch between two different codes, so that you can be sure that if you see something unusual in simulations, then it's not an artifact of the code, but it's reproducible in two different codes. And that's very powerful in terms of getting some degree of verification that what you're doing isn't being unduly influenced by a bug in a code. And lastly, a natural extension thereafter is to be able to run anything through Ace Cloud, and so if one sets things up in just such a way, one can run an arbitrary job on Ace Cloud and choose the type of CPU or compute resource that makes most sense for that job. You can select any instance type from that whole list that Brendan hurt your eyes with. So if you are interested in using it, something which you can get access to right now, it's available just as part of our HDMD toolkit, which you can go and download and install now. If you want to have a demo of it or hand-holding whilst you try installing it, then do catch me afterwards in the break. Any questions?
Any questions for Matt?
Yes. Yes, that's right. It's layered. So in the previous slide where you saw the changing code, so that's the same thing again, just happening in a program which is run from the command line rather than the bits of code.
Anything else? If not, let's thank Matt again. Thank you.
So let's see if I need to, go for it.
Right, our next speaker is Dr. Kenji Takeda, who I've known for quite a long time, but he's an active promoter of e-science, big data, artificial intelligence, and currently is very active in Microsoft research in terms of the Azure for Research cloud. And I'm sure you're going to give us a little talk.
Oh, I hope so. Thank you, Peter, and delighted to be here. One thing that we believe in really at Microsoft is this phrase, let researchers be researchers. Okay. So let the people who are good at what they're supposed to do and what they're trained to do their job. And for researchers, that is researchers. For developers, that's developers. And for sysadmins and IT pros, let's make sure we've got the systems in place for everyone. And we see that the world today really looks something like this. We have the things like SuperMOOC, which are absolutely incredible. We have university clusters, and then we have the majority of users, I would say, who have a laptop or a desktop. And we have a time now where reproducibility is either hard or impossible. And particularly in pharma, we know that we're in crisis around that. And so we believe a shift where the cloud can help, and we still believe very much in exascale supercomputing. There are some things where we need things like SuperMOOC to be able to do those calculations. We learn from those experts. But we can also deploy clouds where we can integrate some of the results from the exascale supercomputers with people doing things on their laptops and share our methods, so that we move into a world of open science where reproducibility is the default. That's what our PhD students should be taught, is not just how to log into the email system, how to do a literature review. They should be taught when they come in and start their PhD that their work must be reproducible, and that's really how we need to change science. And cloud can play a really nice role within that. And one of the things we've talked about really is you only use technology that you trust. And it's not just about compliance. It's about the security, the privacy, and the transparency of what's happening in the cloud. And it's the one thing we pride ourselves at Microsoft, because we've been doing this for a very long time. And particularly where we deploy data centers in region, where we have multiple data centers in the UK. And the reason for that is we've had long conversations with people like the NHS the government. We've worked with the European Commission over many years. We now have GPDR. How many of you are GPDR compliant today with your systems? Okay, you've got 12 months. Kicks in next year, this time next year, okay? We have that now in our cloud, okay? It's very, very important. And in the UK, where we've deployed data centers, we've worked with people who know how important that is. The Ministry of Defence is moving their workloads to our cloud. The National Health Service is moving to our cloud for some of their key infrastructure services. Okay, that is the level of compliance and trust that the Microsoft Cloud has. And we're in lots of regions, we like to say. We're in as many regions as Amazon and Google put together. But it does depend how you define regions. The one thing I would say is we are now investing $3 billion in Europe. Okay, think about that in terms of in our infrastructure. Okay, so the cloud vendors like us and our friends, you know, we really do things at scale, and you can take advantage of that. And when we think about cloud, we think about CPUs. Okay, and we have that all over the place. When we think about, particularly for us at Microsoft, where we're really sort of leading the charge around artificial intelligence, some of these frameworks are really driving deployment of GPUs. And what's interesting, of course, is that people in biomed can take advantage of that. And actually, when I did my PhD in fluid dynamics, we did a lot of the early work around GPUs for CFD. But the thing is that Moore's law's ending, and so we need to look beyond GPUs actually. And I'll talk a bit towards the end about the future of what the future looks like beyond Moore's law and what we're doing with FPGAs across the cloud. And this is my eye chart, similar to others. And I think what I'd like to stress is we often think of cloud at this bottom layer of infrastructure and virtual machines, and that's not really where you get the advantage. The advantage you get is when you move to some of these higher level services that I'm going to be focusing on today, including serverless computing, so using Azure functions to do serverless computing, where we've seen before that can really transform how you think about your research. And we've seen a lot of talk around HPC in the cloud. We've seen a lot of talk about HPC, we've seen a lot of talk about cloud, and when I did my PhD, you know, what's the definition of HPC? I think definition of HPC is at least an order of magnitude more than you can do on your desktop, okay? And you can do that in the cloud. Real HPC, I'm a little bit of a purist, I can be, I would say is low latency. Okay, there's a key thing around high performance computing, high capability computing versus high throughput computing. And with real HPC, you must have an interconnect that can do low latency. Okay, and that's what we have in our supercomputer centers when we go to things like InfiniBand. And people have said that's impossible to do in the cloud. And that has been true. But it's not true anymore. So this is a Formula One CFD case running Fluent, and this is what I used to do before I left the University of Southampton and moved to Microsoft. It's 1,000 cores with over 90% efficiency on a real test case. This is the sort of thing a Formula One team was doing about 3 or 4 years ago routinely. Okay, Ferrari used this code to design their car for Sebastian Vettel. Okay, but the key thing here is the 2.5 microsecond latency. And how do you do that? You deploy real HPC hardware. What I mean by real, I mean InfiniBand, okay, and I mean demonstrable performance. There was this interesting paper, and there was quite a lot of discussion around this paper when it was published, which was a third-party benchmark, an independent benchmark looking at cloud performance. And we quite like this paper, but there was a lot, because LIMPAC is a benchmark which is a synthetic benchmark, but what it does highlight is latency sensitivity, and so it does show that our code is, our systems are good. This H-series VMs that we have do work, but the Fluent I showed you really demonstrates it works on a real code, okay, and when we think about HPC in cloud, you can lift and shift and say, I'm going to put a cluster in the cloud, I'm going to put a scheduler in the cloud. That's not really the point. The point is it's on demand. And so we have something called batch, which basically allows you to wrap an application like you can see in the top right. And you can submit a job, run it, it spins up the cluster, shuts it down. A bit like what we saw earlier But this is baked into our cloud, so you can use this for any application. And what's interesting also now is this convergence of this idea of containers, where rather than thinking of a VM and going from the operating system up and virtualizing, we can start at the application and wrap that as a container. And what's interesting is there's quite a lot of different orchestration engines, and again, we're the only cloud that actually has an open source orchestration engine that supports multiple services, including Kubernetes and DCOS and Mesosphere. And one of the things I should mention is Microsoft is actually very open now. We're actually the #1 contributor on GitHub for open source projects. So we're very much pushing everything out onto GitHub as much as we can there. And when you combine batch and you combine containers, you get this, something we call Batch Shipyard, which allows you on your laptop to create a container and run that container on your laptop, on your university machine, or in the cloud without changing the container, okay, and get InfiniBand performance with GPUs, okay. So this allows you to have that portability and reproducibility with Docker containers whilst getting the performance on the MPI. And then what's interesting, I showed you the benchmarks. We have a lot of benchmarks that show really nice scalability up to 1,000 cores. And it's Biomedicine, and we worked with Peter really to define this case, which is NAMD. So this is these are the standard NAMD benchmarks, okay? And this curve on the side here, which I was just plotting out, I was kind of a bit confused with it, to be honest. So basically, the curves keep getting faster, okay? And that means that it's speeding up even as we go beyond 4,000 cores to the bottom right. That's a big case, a couple of 100 million atoms, okay? The top one I showed to show you I'm not cheating. That green one is the small test case, and it flattens out at 500, okay? Because it's only a very tiny test case, as we expect. But this one shows linear scaling, and I've tried to plot a scalability curve because those right-hand ones, unless you're an MD person, might not necessarily make a huge amount of sense. But this shows dotted line linear scalability up to a couple thousand cores. If I plot the 4,000, the big case, the 200 million, we also get linear scalability, but the smaller strawberry RAM is on 512 cores. The point here is we can run a job on the equivalent of half of an HPC tier 2 machine in 10 minutes with getting linear, actually here's super linear scalability. So real HPC on thousands of cores in minutes is what you can now do. And that's HPC. But in Biomed, there's more to it as well. So I want to talk a little bit about genomics. So we have a team, Ravi here on the right is actually coming over. Hopefully we'll give a talk about some of the work he's been doing on SNAP, which is a new way of doing alignments that's order of magnitudes faster. So he invented that, and then what we did was we looked at some of the processing pipelines, something called BWA. How many of you know BWA GATK? Okay, so we made it go 700% faster because we've got an algorithms team, and so we're now deploying that as a cloud service, and we're doing that with our great partners, DNA Nexus, and we've actually deployed it across the Stanford kind of region with this acceleration. With that level of acceleration, we can start getting more clinical around our genomics. And when we think about things like genomics and imaging, we think about data. And data lake is a refactoring of our Bing search engine backend. So we, as one of the only companies in the world that really understands, exascale data, and we've refactored our search engine backend, and we've made it available as something called Azure Data Lake. When we see hyperscale, our single file limit is a petabyte. Okay? And then you can layer a cluster on top of that, like a Spark cluster or an R cluster. We have R Server. We bought Revolution R, which does enterprise scale R. And then you can publish that as a service, queries as a service. So we've got HPC. We've got exabyte scale storage. We have encryption on that storage where you can hold the keys. Okay? So it really opens up lots of possibilities there. And when we have the data, we can imply intelligence on it. So we saw earlier some great work around CRISPR and how you can deploy functions. Well, if you have your own functions, you can deploy them through this machine learning studio, and you can basically publish machine learning as a service. And what I want to show is how that's been done to help with all sorts of different medical applications. Actually, this is CRISPR-Cas9. This is what CRISPR does. Okay, you get a guard RNA, you attach a protein, you go and you snip the DNA, and you can cut and paste DNA. But there are billions of combinations, and we saw earlier how you have to do that manual search through those things. But by applying machine learning, we can do this way, way faster. And so my colleagues in Microsoft Research have written a ranker for CRISPR called CRISPR-ML. And what they've done is they've deployed that in the cloud so we can do on-target and off-target ranking for CRISPR. And so we can put in our input gene, and then it will run that machine learning as a service through an API to give you those results. Okay, and that's really kind of helping to apply machine learning in that case. I think I'm going to finish off talking about reproducible research. I started talking about reproducible research. We saw Jupyter Notebooks being mentioned. Jupyter Notebooks are fantastic, and typically if you go and you install it on your laptop and you have a web server locally installed, and you can do your Jupyter Notebooks, and then you might have to go and find a Jupyter Hub server somewhere. So it's a fantastic piece of technology, but there is some stuff you have to do under the hood. So what we've done is we've actually got our free service, which is Azure Notebooks. So these are free Jupyter Notebooks in the cloud. And you take your notebook file, you load it in, or you can start doing it. And they're executable. So if you have a notebook on GitHub, it will render the notebook. You can go to NB Viewer and view the notebook. This runs an executable notebook for free, okay, with just a sign-in Microsoft account. Lots of people are using them. So Cambridge University is using this for their entire first-year undergraduate engineering cohort of 350 students for teaching Python. They previously had a server under the desk. They were trying to figure out how to do that. And then we came along with this. Other universities are using it. It's really, really easy to use. And so it's a really nice, again, intro, but again, it's just a free cloud service, so you can just use it whenever you like. And when we go to reproducible research, what's quite interesting is you want to share your data and your algorithms together. And so the team who made the gravitational waves discovery last year have this Open Science Center. And what they've done is they've taken the data from that discovery and they've put it into Azure, and then they've also published then on the right their Azure notebook, so that you can go to this Open Science Center and actually reproduce and rerun the analysis of the gravitational waves discovery last year. That is open reproducible science. And it's on the cloud on Azure, and you can do it just from a free Jupyter Notebook. So it's really interesting how this sort of combination of technologies where they put the data in the cloud, we've got a hosted notebook there, and we're starting to try and enable this open and reproducible research. And I hope you can see how the cloud gets over a lot of those barriers that you need to do that. I do want to talk about this, which is what happens when Moore's law runs out. We know that Moore's law is ending. There's a joke that is hopefully funny, that the number of people who say that Moore's law is ending doubles every 18 months. Okay, so, but it will end. And for you, using the cloud, it's not a problem. Because cloud providers say you can have an infinite amount of computing. Okay? For the people who have to provide that, it's a nightmare. Okay? So Doug Berger, who's one of the world leading experts in computer architecture, has been thinking about this for the last, actually, I think 2010 he started looking at this. And, looking at all of the different possibilities, and basically we've taken a bet on programmable hardware. So what he's holding there is an FPGA card. It's got an Intel Altera FPGA on it. And we did a test where we put those into our Bing search engine, and we ran a small test of these on about 1,600 servers, and we could double the performance of our search engine for just a 10% increase in power. Okay, and you think about that, it's really, really powerful. And we did look at GPUs. We have GPUs, so we understand that, but we've decided that the FPGAs are where we want to go. And when we deploy the FPGAs, there's lots of different ways you can do that. You can deploy them as just compute accelerators like GPUs, and that's great because you can do some acceleration. We've done something slightly differently. We've got a compute layer around the outside. We've got a network layer, and this is supposed to represent a data center, okay, where we might have a few 100,000 servers. What we've done is we've inserted the FPGAs between the servers and the network. It's actually in front of the network card, not behind it. Okay, that means that we can communicate any to any. It's called a bump in the wire, this architecture. So you put the FPGA on the wire. So we can do things like accelerated networking. So we have very low latency, called Azure Enhanced Networking, high bandwidth, low latency, but not just InfiniBand, but this is across our entire server infrastructure. And so you can do very interesting things with that. And so definitely talk to me about that if you're interested. We can give you access to some of these FPGAs. But the interesting thing is we can run across the data center with about a 10 microsecond latency. Okay. And this isn't theoretical, this is deployed. We did an experiment where we said, what can we do? We did machine translation, and we took machine translation and put it onto the FPGAs. And we could translate the whole of Wikipedia in a tenth of a second. Okay. So it was an exascale computation. It was not floating point, but it was an exascale computation that we did. And so hopefully you can see how our investments in cloud technology are really pushing the boundaries, and we're really thinking ahead around architecture for this. I want to finish off really talking about what we call research as a service. So this is the idea of making the things you're working on. In this case, Jasmine Fisher in our lab is working on executable biology. So how do we look at pathways in cells? And she's developed a tool with colleagues called Biomodel Analyzer, where you can go and you've got a cell and you can put in DNA and proteins, and you can, essentially what we're modeling is the equilibrium state. Yeah, and taking computer science technology, actually some of the technology we use to get rid of the blue screen of death, so we can actually prove that programs run to termination, okay, which causes blue screen of death as your device driver doesn't actually run, it gets into an infinite loop. Applied that computer science to biology, because skin cells, if they don't reach equilibrium, develop melanoma, because they don't equilibrate. And there's a tool on the web that you can go to Biomodel Analyzer, and you can go and you can play with this. And so again, it shows how we can make our research available through the cloud. And some of our friends in the Netherlands have been doing something similar and been delivering research as a service in a very interesting way, and I want to let them tell you about that.
Is basically bringing together scientists in all kinds of disciplines in the life sciences and biomedical sciences. A colleague of mine met in the south of France in the workshop, and already we see the end of combining computer science and life sciences in the scientific area.
I've met the audience, which is a professor at the University of Cambridge. So he was trying to understand how different genes in blood cells interact with each other and might lead, for instance, to diseases such as leukemia. We developed a tool called Combine to try to understand how different genes can regulate each other. When we developed Combine, we were wondering whether we could apply the same technique that we use in leukemia also in animals. Therefore, we contacted PG, and they were excited about it.
PG does research to support seed breeding companies to develop new and improved crops, higher yield, better nutritional value to their crops.
We're excited to work with Nicola to see if the Combine tool can be applied to plant genetics. Currently, we're only looking at genes themselves. With this tool, we're also looking outside the genes. How do other parts of the genome, of the DNA, affect a certain trait? It gives us more insight into how genes work. We can provide this knowledge to plant breeders to help them make better crops.
I wanted to make this tool available for other people to use. Since the beginning, it was clear for us that Azure would provide the scalability and robustness necessary to deliver Combine as a research as a service. We created that because we said there was not enough software engineering in life science, and we wanted to empower life scientists with innovative tools that use state-of-the-art software engineering. The challenge of this century is transforming life science in an engineering process, and to do that, you need to bring engineering into life science. And although probably I would not see the end of this journey, I would like to participate.
So it shows how he was doing his research as his PhD, and he realized he wanted to share his research. And that's why he built Combine. And on the back end, where he was in University of Amsterdam, they had a cluster, they had an HPC cluster, but it couldn't run on demand because when you click that button, it has to spin up a bunch of machines, and that's what Azure can do, and is actually re-implementing this with a batch system that will automatically fire up a cluster. So I've talked to you a lot about what you can do with Azure, but where do you go from here? So as part of our partnership here, if you ping me, I can give you some instructions to activate a slightly bigger than normal trial so you can play around with some of the things that you've seen. And that's quite nice just to get you going. But we also have our program of awards where we can give you larger chunks. And we're starting to work with quite a lot of people to take this real HPC where you see my benchmarks. And you can actually try it yourself and really see how this cloud HPC can work for you. There's no one solution fits all. We've built what we think is something that's very, very useful, and we want to work with you to help take you on that journey and see how you can do more epic research, as we like to say. So, thank you very much.
Thank you. Anyone want to pose questions for Andy?
I have a question. You started with the theme of reproducible research. The question itself is a bit conjectural. You also mentioned MRR and Microsoft are open, which is distributed through Conda with one channel. How does Microsoft, if that is Conda as an environment for reproducible research, are you going to keep using it, or
well, I guess
things like machine learning framework, for instance,
yeah, I mean, we try and have platforms there that people can then build sort of frameworks on top of. So we try and make sure that we have a lot of open source tools there. So that's a good thing. But the integration, really, we're sort of interested in working with projects who want to turn that into more of a service. So we're a sort of platform provider, so we can provide a platform for science, and then other people, we can work with other people to do that.
I guess to replace that, do you see Conda environments as the way to go? Way more like when Intel, IBM recently announced that they're going to be using Conda as well.
Yeah, I mean, I guess, there's no magic bullet. So I think we have to just support as much as we can and see how the community, because there is no magic bullet, right? There's nothing that's going to solve it. People are saying Docker containers are going to solve everything for reproducibility. They're definitely a useful technology. But one of the reasons people use MPI is because MPI is still around. Which technologies are still going to be around in 10, 20, 30 years? So I think it's just a matter of just seeing where the community goes and having as many tool sets there to make it easy for people to experiment, I think.
Yes.
You mentioned one important issue, reproducibility. So I think that it is really in a situation when research is going in such a way that people develop a lot of models and change simulation conditions, having something like this is really making something, making modeling in chaotic world, which is possible to have in to kind of governance system of the science to have ways to just develop
So again, other people build on top of that. There's some interesting work at Newcastle with Paolo Missier where they've built a sort of workflow system that has provenance built in. And there are platforms, and I think that's why DNA Nexus and others kind of have provenance, or workflow provenance. So you need workflow provenance and data provenance. You can do version control, okay, so you can have some provenance of things. And so we certainly see people using a combination of different technologies like GitHub and notebooks and things, but provenance is a tough one. And I think there's a lot of research going on in that area, and the cloud definitely helps with that, I think. And again, we kind of rely on other people to work with us on that.
Okay, well, let's thank Andrew one more time. We just swap over here. Okay, our last speaker in this session is Dr. Alessandro Combini from DNA Nexus. And I think you may tell us a bit more about yourself, but you're the scientific lead for the Europe, Middle East and African region for DNA Nexus. And DNA Nexus is an associate partner of Biomedicine, just to make sure everyone is aware.
Thank you, Professor Carney. Thanks to the organizers for inviting me. Can you hear me well on top? Excellent. As an introduction, I'm Alessandro. I'm a scientist from DNA Nexus, from our European team. I'm based in Cambridge, but don't be fooled by my accent. I'm actually Italian. So in the next half an hour or so, I will introduce you to DNA Nexus as a company, as a platform, and most importantly, as a network. And you will see why at the end of this presentation, our nature as a network is probably our main value. And the company itself was founded 8 years ago as an academic spin-off. Today, there are 90 of us. Of these 90 people, around 52 are coders. Of these 52, 20 are bioinformatics and computational chemistry scientists, to give you an idea. And actually, until a few months ago, our sales team included 2 people. And the reason is that while other bioinformatics company will send a software engineer or a salesperson to talk to a customer, we always focus our interactions on customer problems. We heard from both from Amazon and from Azure today how important the scientific question and scientific discovery is rather than just infrastructure. And as a company providing secure and compliant cloud infrastructure, for us, our main interest in our interactions with customers is really being helpful and helping them solve their problems. And so at the science team I'm a member of really interacts with customers on a daily basis, trying to understand what they need, what solutions they're looking for, and together with our partners, we work to make these solutions achievable on our platform. We have 5 offices, Boston, Mountain View, our main office in San Francisco, our Cambridge office, and another office in Shanghai. We have more than 70 enterprise customers and around 10,000 users, and these numbers might seem low compared to others we heard, but the scale of what these users are doing is quite interesting. We work with 13 of the top 20 global pharmaceutical companies, and I will anticipate that in a few weeks you might hear of the name of the 14th, and it will be quite interesting to hear. We are leaders in for genomics infrastructure for American institutions like NIH and the FDA, and we'll get back to this in a few minutes. And as a company, as a cloud-based platform, we are multi-cloud and multi-region, meaning that we work with different cloud providers, and for each cloud provider, provide different regions. Our original deployment years ago was based on Google Cloud, and Google is still one of our backers. And for a number of years, we worked with AWS, as they have been leaders for years in the public cloud market. And 2 years ago, we started our partnership with Microsoft. And today, in DNA Nexus, you can have a number of projects in the same environment for your own, under your same profile, and access projects based on AWS and Azure. And we're really privileged to be working with companies like Amazon and Microsoft because they share our values regarding security, compliance, and most importantly, being useful for our customers. And this is really something that is at the core of the interactions we have with them. DNA Nexus initially tried to solve a basic problem, secondary data analysis. As you might have guessed from our name, our initial interest and background was really around DNA sequencing analysis. And secondary analysis, going from a sequencer, from raw data, to analyze variants or expression counts was really the original problem we solved. And as we were working on this problem, and as I said, the generation of sequencing data got cheaper and cheaper, the attention moved from creating this data to processing it and analyzing it. And as the cost went down, the scale and the scope of projects in the genomics field escalated. And you go from something like reprocessing the entire cancer genome atlas, tens of thousands of samples, 500,000 of jobs. You go to an interaction like the one Regeneron has with Geisinger, Regeneron providing genotypic data, Geisinger with the phenotypic data. This is really the largest geno-pheno integration project that you can find around, and it's done on the Nexus scale. And you might have heard a few weeks ago that GSK here in UK is collaborating with Regeneron to analyze 500,000 exome samples, which will go in the UK Biobank. This data will be processed on Nexus, and the interesting thing is that once the data is processed, the UK Biobank will make it available to interested parties within 9 months, and through discussions, some of the other potential collaborators who are interested in accessing this data already have work done on the Nexus. And when the time comes to share this data, it will be a matter of setting the permissions and sharing samples with between pharma partners or institutional partners. And of course, there are even more ambitious projects. We heard the announcement of AstraZeneca's genomics initiative, 2 million samples. This is still to come, but you can see where we are going, and it's only a matter of time before even more ambitious projects come forward. And you can see that there's really a need to solve the problem of handling and processing this huge amount of data so that we can all focus on the scientific question. And this is the problem in Nexus is trying to solve at the beginning. It's a solved problem. Now the question is how to move forward from the end point of this analysis. And I will get back to this in a few slides. I will just mention that as part of our growth, we created a partnership with Wuxi Nextcode. They are one of our investors, actually. They sit on our board of directors, and with them we operate in China. And so, of course, one of our regions is on AWS China, and if your data has locality restrictions for China, of course, you can do this. And for that region, we work with Wuxi. In this section, I will introduce the platform itself. As a company, despite the name, despite the bioinformatics, our main selling point is really security and compliance. There is no other company in the market for bioinformatics which has our same level of investment and excellence for data security. I've been in the cloud bioinformatics market for a few years, and you will be surprised by how many companies are out there who claim, we are secure, you can give us your sensitive clinical data. The truth is that these companies are using maybe AWS, and they say AWS has ISO certification. We use AWS, therefore we are certified ourselves, and you can just put clinical data on our platform. Just believe us. And that's not the case. There's a lot more work that goes into that. And our platform has been really designed and built from scratch around the requirements of the ISO 27001 certification. Our staff is trained according to the requirements of the American FedRAMP to have authorization to operate. And other platform features like having immutable data, multi-factor authentication, single sign-on, full auditing and full provenance of everything that you do on the platform. This is all based around requirements for certifications like CAP, HIPAA, GCP, and so on and so forth. This on top of the various certifications of the cloud providers. It's these synergies that really makes us market leader as a cloud informatics platform in terms of security. And I can guarantee that when the time comes for security auditing, it will be very unlikely that somebody else can catch up with us, at least for now. And I will probably skip this. The platform, as I mentioned, is multi-region, so you access and consume storage and compute. Depending on which cloud provider and region you selected, you might be using blob storage on Azure for one project, or S3 storage for another of your projects on AWS. Similar thing for compute for instance types. And you interact with the platform through the web UI, and from the command line. Everything can be done programmatically. If you have to deliver process data to some of your collaborators, in theory, you might as well have a cron script which finds new data in the output folder of the sequencer or in some Dropbox storage. This is uploaded on the platform, some workflow is just launched, and your collaborator just receives a notification email with a download link. This is really something that is fully automated at this point. This is how the web interface looks like. On top you can see buttons called projects and apps. A project is the basic environment where all your work happens. Everything you do refers to a project, and this is what projects, as I mentioned, can be based on different regions. Apps are really programs available on the platform. These include open source and commercial softwares. And actually, if you want to share your work, your algorithm, with a restricted group of users, you can do it by setting the right permissions in your app. If you want to publish your new method and share it with the world, you will be able to put it as a public app in the catalog. If you want to do beta testing with a restricted number of users, you can have the possibility of restricting access. And this is how a couple of steps for a basic pipeline look like. This is actually something that Kenji mentioned previously, BWA for aligning sequencing data and GATK to perform mutation discovery. And on the left you have inputs, on the right you have outputs. And something I should mention, these apps, so the black boxes, are the amount of work that goes into integrating your favorite tools into an app depends on your requirements. Inputs and outputs depends on how you design the app. We recently introduced Docker support as the first step to generalize containerization support to further facilitate the porting of your favorite tools on the platform. There are a number of tools, for example, PacBio's smart analysis tool for ultra-long reads, which are notoriously difficult to install, come with a large number of dependencies. And our software development kit helps you bundle the dependencies together, defining them in a relatively simple way, and makes you not worry anymore about installation pains. Moreover, it is possible to configure your favorite specifications in the interface of these apps. You might configure memory, processors, and storage, depending on your needs. And of course, the cloud, by definition, really provides compute on demand. This is genome assembly. If you're not familiar with it, it can be quite expensive computationally, especially for PacBio. And something we sometimes do with our partners, we port their tools on the platform, scaling up what these tools can do, going from a local server to the cloud, having as many jobs running as needed. And all of this comes with a flexible permission system. You can define roles with 5 levels of permissions. Level 0, of course, no access at all. Viewers can only read data. If you have to share some let's say a master list of workflows with your colleagues, they can have read-only access, or if you want to share reports, they can have this level of access. Uploaders can just upload the data, contributors and analysis, administrators edit all these memberships. And most importantly, In collaborations, funding can be a crucial point, and our permissions also allow you to define which users can access credit from your organization. Actually, and this is also extended to the software you're willing to share. This is just another example of what I just mentioned. Here you have on top right, sequencing service provider. They can only upload data and they consume your credit doing so, but they don't need to buy any credit themselves. Bioinformaticians are running analysis with contribute permissions, and clinicians might look at the data. We actually started working with some provider of clinical data analysis, and they are using us integrated together with QIAGEN's Ingenuity pathway analysis, and they automated the workflow of the data. The sequencing service providers they work with have upload permission. The team, the bioinformaticians of this company will contribute. They run the analysis, and then the clinicians in the hospital just recover the reports. And this security, this flexibility in permissions make it possible for companies like Natera to perform non-invasive prenatal testing, for example, by collecting data from multiple small clinics, pulling it together on the platform and delivering reports back, all again in a secure environment. And for genomics analysis, for genetic testing, really one of the main bottlenecks is patient consent, and it can be quite time-consuming to acquire it. So you really need a centralized and secure platform to collect all this data, and it's the small clinics, the clinicians working in these distributed clinics which have access and are able to give consent, to get the consent. Of course, this opens the way for interesting partnerships. We are a partner of Ensemble MD, and our science team has integrated UF back on the platform. It's possible to use our to run it from our web UI as needed, and of course you don't have restrictions in terms of how much compute you can access depending on the design of your experiment. And this is actually very important for us because despite our name DNA Nexus, we are completely agnostic with respect to the data and the software types you can process on the platform. And before somebody asks, an American blogger copyrighted Data Nexus, so we can't do that. So sorry about that. But thanks to EFBAC, we are moving into computational chemistry. There is actually, we work a lot with pharma companies. As you can imagine, genomics is only a part of the analysis they do, and computational chemistry is helping us grow immensely, so we're very thankful for this kind of partnership. It's really great. And to summarize what I said so far, this is a scheme of the structure of the platform. At the bottom, you have the different cloud providers in the different regions: Amazon US East, China, and Frankfurt for Europe, and Microsoft Azure now just in US Central. We deploy new regions depending on business cases. We might deploy in the near future on Singapore and Australia, for example. On top of this, you have the core services, single sign-on, our security layer. On top of this, data and collaboration services, the permission systems I mentioned. On the top left, Elastic Compute Service, compute on demand. Developer services, our software development kit to help you port your pipelines. On the top left, scientific pipelines, something like what I showed before with BWA and GATK. However, as I mentioned, secondary analysis for us is a solved problem. It's not that interesting at this point to just process pipelines on the platform. There is much more that can be done for scientific discovery. And in yellow, you can see where we are going in the future. We are developing technology to facilitate the integration with software vendors and third parties. We are in our first step is introducing stacks. A stack in general is a third-party software which will run in a secure and compliant way, encapsulated in our environment. So you might have some commercial software which by itself is not secure and compliant, but launching it as a stack on DNA Nexus will give it the level of security. Thanks. So I will. In the last 5 minutes, I want to mention the most interesting part, the network. Something interesting is that as projects started being developed on the platform, institutions, companies like Bush in Xcode or Cambridge Epigenetics here in UK or Regeneron, they eventually said they found out that others were on the platform and they started working with each other. You can see Regeneron and Geisinger in their own cluster there in the center. But as more and more data goes on the platform, as more people are processing data, collaborations become easier and easier. And I already made the example of Regeneron and GSK, who will be working together. And if Regeneron or Novartis want to have access to the data, they might require it to access to a UK biobank, and the data will already be on the same platform they already use. I probably skip this. Another example of a collaboration that can be made possible with this network, the image consortium, where you have 25,000 samples being processed by 9 partners with 2 centers, the Baylor College of Medicine, the Broad Institute, grouping together some of these partners. As you can imagine, for a distributed collaboration like this one, you do need security, you do need compliance, you do need to make life easy for the researchers who need to access this data. This goes well beyond running a pipeline. And as a company, our culture really is based on, we strive to work with everybody. We really have no exclusivity, no limits. We really want to find the best possible solution for the scientists and researchers who use the platform. We work with a number of infrastructure providers. We integrated different LIMS systems. We had some companies like Illumina or Oxford Nanopore might want to develop their own platform and have all the data centralized, but we are open to all sequencing data or all other kinds of data. And you can integrate different technology on DNA Nexus without any limitation from our side. And downstream to us, this is where the partnerships come into place. We might work with companies like Linguamatics for text mining, Giggle Genomics for metadata profiling, Ensemble MD for UFBAC, StationX for interactive visualizations, Bush in Xcode for tertiary analysis. We work with different partners, and when one of our customers is asking us, could you work with this third-party vendor? We really work together with the vendor and our customer to make sure that we can provide the best possible solution. And as our stacks technology develops, we will be able to eventually launch custom architectures on the platform, customized for each of these softwares. Our first proof of concept this year, in the next few months, will actually be Jupyter Python notebooks. It's a small example, but still you will be able to use Python notebooks in a secure and compliant environment. And after this, we're already working on bigger, more ambitious stacks, which will involve these partners. 2 more minutes, excellent. I'm going back to this slide. You can see the light blue box on the top right. DNA Nexus is actually a twofold offering. You have, from data collaboration services to the bottom, you have the core infrastructure, and on top you really have the web interface. And something we do for our partners in some cases is creating a dedicated web UI, a portal or a branded page in some cases. But for more ambitious projects like the Precision FDA, the White House hired us as a contractor to build a web-based platform for genomic medicine. When you go on the Precision FDA website, this is actually DNA Nexus in the back end. And for other companies, for example, we are creating a microbiome dedicated platform. And I think I will skip this. And as our marketing team loves saying, DNA Nexus today is pushing the limits in genomics medicine. Thanks, I will welcome any question.
Any questions for Alessandro? I see another one here.
You mentioned that you started working with Google Cloud, and then in the last slide, it wasn't mentioned anymore. Are you using Amazon and Microsoft? Why did you drop Google, if you don't mind? Google.
Yes.
The question, I'm not sure everyone does hear this up at the top. The question is why Google
was dropped out as a cloud provider.
Well, we haven't heard too much from Google, but we have heard from AWS and Microsoft.
Yes, I will say the main reason is that it was a matter of timing. The current today's version of DNA Nexus is the second incarnation of our platform. The first one was based on Google Cloud at the beginning, and it was also entirely tailored around experimental biologists with minimal coding knowledge, single button pipeline, so on and so forth. Today's platform is as flexible as possible. The ideal user has some coding or at least software user expertise. So this new version is 4 years old. And that 4 years ago, when we started building it, it happened that our customers were demanding AWS. That took priority. And today, customers are also asking us to use Azure's new technology. And this is just, if somebody asks us for Google Cloud, we already have the internal know-how to deploy a region there.
Can't see any other questions. If that's the case, let's thank Alessandro again. And of course, I want to thank all the speakers because they've worked extremely well to get us ahead of schedule. Everyone should be happy about that. And so we're going to go for a tea break, but I think we can come back at 10 to 4 rather than 4. We will be able to get away at least 10 minutes earlier. Just to remind you, if you wanted to pose any questions for the panel that's coming up at that time, you can pop your question into that sort of ballot box thing at the back of the room, and we'll see you at tea and then back here. Thank you very much. You're on the panel. Yeah, sure.
It's a website. I think the issue is feedback on how No, it's the web, it's that web page. Right there on screen. But there is a paper which explains chat. So it's an active process. If you want to do some stuff with Whisper, like they might say, hey, yeah, let's put together they're actually so, yeah. Which was great. Hard, right? And actually have web Yeah, we did a trick. Anyone idea with the logo? We did the same thing. Program. Pretty fun. How do you see it? Oh, no, we're going to go to university and get a microscope. But, so we're doing a lot of fun stuff. We actually, some of the IP folks are Yeah, we had a conversation about how he's thinking about I know he's doing some stuff with
Yeah, we have
that's good though. I guess we found it useful.
it's not in the Singapore, it's in
Oh, I see.
and I'm not doing it, but that is basically startup. So that's my business. I used it a couple of months ago. Basically, me and one other fellow, we did machine learning.
Oh, okay.
Spinning up GPUs.
Okay. Yeah.
But now we oh,
okay.
CT,
Oh, we did segmentation. So I think we owe the same thing.
That was a while ago.
Well, I mean, it's
yeah.
It wasn't a challenge.
So we got graphics on GPU workstations. Yeah, we were using those and we switched it to them.
Yeah.
And therefore, I just people
I think we're talking Where you based this
primarily buying stuff.
Okay, because I think we're doing I think one of the sponsors is because the machine learning point C. Okay. Yeah, I think storage. Yeah, so it's still going. The time.
And I was doing whenever I did my practice course,
Well, Garth put the Cambridge course on it. It's got a whole
I think I probably still want to start with one home with and then move on into it's a 3-day course. I don't know what my question was. I know it's not